That works well. Perfect. Like I was saying, I have a quick announcement to make before I introduce our speaker for the day. You may have noticed that we've upgraded from our usual cookies to donuts this week. And for that, we have Dr. Walter Herzog to thank. Not because he bought them for us, but because we're celebrating his birthday today. He turns another year wiser on February 19th, but since he'll be away next week, today seemed like the perfect time to celebrate. So thank you, Walter. And in the spirit of his birthday, all the HBL rats are welcome to enjoy some high-fat, high-sucrose treats sitting back there on the table. All right, moving on. Our speaker for today is Donald Golden, who is a PhD student in medical sciences at the University of Calgary, where he specializes in joint injury and arthritis research. His research focuses on joint function, physical activity, and exercise in individuals with hypermobile Ehlers-Danlos Syndrome. He is co-supervised by Dr. Renita Minocha and Dr. David Hart. Donald started his academic journey at Mount Royal University, where he earned a Bachelor of Health and Physical Education with a specialization in athletic therapy, graduating in June 2023. He then started his graduate studies as a master's student in August 2023 before transferring to his PhD in December. Beyond his research, Donald has some impressive extracurricular activities. He holds a second-degree black belt in Taekwondo, and he enjoys fishing as a way of relaxing and unwinding. Today, he will be presenting his talk on muscle tendon function in the hypermobile subtype of Ehlers-Danlos Syndrome.
Excellent. Thank you very much for the introduction. And thank everybody for having me here today. I appreciate the opportunity to come and talk about some of the work we've done. And so again, this is some of the work we did back at Mount Royal University when I was in my undergraduate studies. And really talking about muscle tendon function in hypermobile Ehlers-Danlos Syndrome. And we'll explain what that condition is and everything here as well. If I can figure out the clicker. So just to start, I have no personal disclosures with the research that we did. The study was performed at Mount Royal University, as I mentioned, and we did receive funding from the EDS Society's Clinical Major Grant to perform this work. So I'll quickly go over what is Hypermobile Ehlers-Danlos Syndrome, or HEDS, then can I go over the two aims of this project. We want to look at characterizing muscular weakness in this condition, including the foresight properties of muscles in these individuals, as well as looking at muscle tendon dynamics and energy cost during walking in these participants as well. And so to kind of bring some context to it, we know that movement is really a cornerstone of life and enables us to create nourishing experiences and fulfill activities necessary for daily living. But this isn't an inherent thing. We know that for some individuals, your ability to move is compromised by your own body, by the structure of your own body. This can be the case with some individuals with hypermobile Ehlers-Danlos syndrome. And so this hypermobile EDS, as we've termed it here, HEDS, it's a connective tissue disorder, which is characterized by alterations in collagen and pretty much any structure that can be made of collagen. But it's really characterized by these hypermobile joints. As you can see here, we have elbow hypermobility here, the knee joint, the wrist and thumb, as well as the spine as well. And so this is really this characteristic of the condition is really flexible joints. As well as having joint flexibility, some of the biggest things that people have are chronic pain, really excessive fatigue, really frequent joint injuries, including joint subluxations or dislocations. This could be a really limiting thing for these individuals. Something as simple as bending over to pick something up off the ground may have to dislocate your hip in some instances. And so it can be quite severe in those cases and quite limiting. And so, like I mentioned there, it can result in some limitations in physical function. And generally, these people are inactive and have really intolerance to exercise and activity. There's also many other associated comorbidities and other conditions that these individuals tend to have, such as orthostatic intolerance, autonomic dysfunctions, mast activation syndrome, a whole bunch of other things that go along with it. So it's often not just hypermobility in and of itself. This affects about 1 in 600, 1 in 900 people, sorry. And this is kind of the most recent population data out of the UK. This is thought to be similar prevalence here. And of those affected, about 70% of those diagnosed are female, so a higher prevalence in women with this condition as well. And so there's a bit of a spectrum in terms of kind of clinical presentation of hypermobility. And this is kind of supposed to give us a framework of kind of what that looks like. And so on the kind of the very left side of the screen here, this is just asymptomatic generalized hypermobility or joint hypermobility. This is kind of your athletes that like seem to be double jointed, like your flexible gymnasts, things like that. People who don't really have symptoms, just really flexible joints. They would describe themselves as being like double jointed, for example. As you kind of move along the spectrum here, you get generalized joint hypermobility, which is a clinical diagnosis of hypermobility if they meet a certain amount of criteria. Then as you move along the spectrum, you have increased symptom prevalence and severity, so more of that chronic pain, fatigue, other clinical manifestations of these conditions. That's kind of characterized by this HSD or hypermobile spectrum disorders, which is a broad umbrella of different phenotypes and presentations that hypermobility can present with. Then on the far end of the spectrum here, what's just kind of the most severe and impacting in this case, is Ehlers-Danlos syndromes. And there's actually 13 different subtypes of Ehlers-Danlos syndrome. We're just looking at the one subtype today. HEDS is the most common subtype of hypermobile or of Ehlers-Danlos syndrome. And it's also the only one without a confirmed genetic cause as well. And so it's thought to be just due to the heterogeneity and multiple genes involved with it potentially. But that's kind of the framework of hypermobility that we're kind of looking at here. And so there's really the impact of connective tissues, because that's ultimately, like I mentioned, what the cause is for most of these connective tissue disorders. So any tissue like your tendons, your muscles, really anything that's made up of collagen can be affected in these conditions. When we think about tendons, this is kind of just a diagram showing kind of a hierarchical structure of tendons. And really kind of the interesting thing I think here is when we have these alterations at, the most cellular level, how does that manifest at the tissue level and at whole body function? And really that kind of begs the question of how do these alterations in tissues at these different levels impact physical function at kind of the more global level. And so for individuals, as we mentioned, this really can be potentially debilitating for someone, affecting their quality of life and their ability to do activities of daily living. It is a bit of a spectrum in terms of how people present with the severity of it. Some people are really limited by this condition, whereas others are able to function relatively well. So there is a bit of a variability in terms of how it presents that way. But one of the thoughts is that a way that these symptoms are manifested is through this increased tendon compliance, which would require additional muscle shortening to operate these joints, as well as, and with more muscle shortening is going to be a higher energy cost. And we think that that would be associated with more pain, more fatigue. Another thing that has been looked at but not characterized is the mechanisms behind muscular weakness. We know these individuals are weaker, but we don't know why they're weaker or what makes them weaker. And so there's a couple of different factors that could explain muscular weakness in these individuals, one being muscle force length properties. As we know, the amount of force you can generate is really dependent on the amount of overlap between those actin and myosin myofilaments at the sarcomere level, and that overlap is dependent on the length of that muscle fiber, and so that can be dictated by that force length relationship. Muscle architecture is another thing that can influence strength production, and so there's a positive correlation, between muscle thickness and pronation angle that can influence strength. As well, I skipped ahead too far. As well as muscle quality, and one way to look at muscle quality is using ultrasound. You can use a histogram analysis, which we'll dig into a bit later. But it kind of characterizes the quality of their muscle tissue. So is there more fibrous tissue in this muscle? Is there more intramuscular fat deposits here? Things that would also impact strength measurements. So that's another way you can kind of dig into the mechanisms for muscular weakness, to be looking at kind of these factors. And so where our work comes in is we wanted to focus on the ankle joint in particular, because that was kind of one of the main research specialties of our lab at Mount Royal. And the first aim of this was to really look at, okay, what's making these individuals weaker? Of these kind of reasons we listed out, can any of these explain why these individuals who are inactive and having these symptoms, we figure out why their muscles are weaker? Because that would inform, targets for interventions for strengthening, other things to help improve function of these individuals. The other thing we wanted to look at was how does muscle tendon dynamics during activities such as walking impact their pain and their energy cost, and because that could be implicated for symptoms such as fatigue. And so really kind of diving into the mechanisms from the muscle skeletal tissues that could be impacting their symptoms and their physical function. And so how we went about doing this is we'll talk about kind of each of the aims particularly. The first aim, we wanted to look at muscle weakness, and we had them on this isokinetic dynamometer here, as you can see. We had their ankle joint affixed here, and we had some ultrasound probes, one on the medial gastroc muscle, which you'll see images of in a few slides, as well as we had another ultrasound probe where the medial gastroc meets the Achilles tendon, which we call the muscle tendon junction. And so then we can visualize kind of what's happening at the muscle and the tendon level during these contractions. And so when we had them on this dynamometer, we're interested in a few things. We wanted to characterize the force-length relationship with the medial gastroc. So we wanted to bring them to different joint angles and figure out when they're at different classical lengths, what force they can produce. We wanted to look at the Achilles tendon stiffness. We wanted to look at some reasons behind that muscular weakness. So looking at their muscle thickness, their pronation angle, and that muscle quality. We did this all during a single testing session. We first did a couple of questionnaires to kind of characterize quality of life in our participants. So SF36 is a questionnaire that kind of looks at probably different domains of health and quality of life, as well as a function index and fatigue severity scale that kind of capture more function and symptom measurements in our sample. We did some passive range of motion testing. So when we attached their foot into the thing here, I'll use my pointer. When we attached their foot into the dynamometer here, we had them set their range of motion actively. So they did maximum dorsiflexion, maximum plantar flexion. That defined a range in which we would rotate the ankle. And so we passively rotated them, to look at a couple of different properties there. Following the passive rotations, we did maximal voluntary contractions, or MVCs. And we did these at 20% increments of their range of motion. So maximum range of motion we defined as being plantar flexion, 0% being maximum dorsiflexion. And we randomized which 20% increments we would do, so 0, 20, 40, 60, all the way to 100. And we would look at the force length properties at each of those joint angles. For the second aim, we'll talk about the methods of this and we'll get to the results. But after doing the biodex testing there, we had them on a treadmill. So then we wanted to look at the muscle tendon function during walking, as well as capture the energy cost. As you can see, we have them hooked up. There's a bit of a metabolic mask you can see here, where they would capture their inspired oxygen, expired oxygen, CO2 content. And that would go down. There's a mixing chamber behind here that you can't quite see. That's where we're capturing those measures. So again, in this part of the study, we wanted to look at pain at different speeds of walking. So how is pain influenced by walking at different speeds? We wanted to look at the energy cost it took to walk at various speeds. Looking at different things like tendon energy storage and how that might be different between participants. Muscle activation during gait, as well as muscle forces and muscle energy costs. Because we want to look at is any differences we see in the total energy cost of walking, can that be attributed to differences in metabolic energy costs, or muscle energy costs, sorry, at the ankle joint. Because we did this in the same testing session as the strength testing we just did. Once we finished the strength testing, we brought them over to the treadmill. We did them determine their preferred walking speed, which I coined PWS here as an acronym. And essentially we had them walk for 10 minutes and they would go faster, go slower, and figure out what speed they preferred to walk at. And we would use that speed to kind of figure out our next trials here. Once they figured out that preferred walking speed, we had them walk at 3 different randomized speeds. 100% was their preferred walking speed. We had them walk a little bit slower, so 80% of that speed, and a little bit faster at 120% of that speed. So kind of look at how pain and the different muscle tendon function was impacted at different walking speeds here. We randomized which of those speeds we did first at each trial, and each one was about 6 minutes. And we also looked at how pain changed after each walking trial, measured using a visual analog scale, or VAS, as you see here. And I just measured from 0 to 100 millimeters and physically marked it on a sheet. And so looking at some of the individual measurements we took, so we took tendon measurements to look at the Achilles tendon moment arm, as we use that in our calculations for forces, for muscular forces. And you can see here, this is just a schematic of how we calculated that. So this is during the passive rotations on the dynamometer that I mentioned before. And what we can do is for a given change in ankle joint rotation, there's going to be some elongation of that tendon, and we can use that to calculate the moment arm of the Achilles tendon. We looked at plantar flexion forces, and we wanted a method to compare the forces that they were producing during their maximal voluntary contractions, as well as the forces they're producing during walking. And so we were able to do this using these force insoles. So they're commercially available force insoles that let us sample plantar flexion force at about 100 hertz. And what we did with these was we used an inverse dynamics approach to calculate muscle forces based off of this. And we use, as I mentioned, we use these during both the maximal contractions as well as during gait. Then we compare the forces they're producing with each part of the testing. So we're seeing here, if it comes out well, this is an image of the medial gastroc. I'll use my laser pointer again. Medial gastroc here, and this is the Achilles tendon. And so this is our ultrasound visualizing the Achilles tendon junction. In this case, this is a slowed down visualization of a maximal voluntary contraction. So you can see here, this is as they're plantar flexing, as they're pushing into the plate, that's when that muscle contracts. And we're able to look at, in this case, the elongation of the Achilles tendon from that junction as it contracts there. So some really cool visuals. And so from this measurement, essentially, we're able to look at calculating Achilles tendon stiffness. So we chose one of our MVC closest to 90 degrees of the ankle joint. And from that, we used the slope of tendon elongation, so how much is stretched, and the force that they're producing during that contraction to look at the stiffness of the Achilles tendon. We're also able to use the same images, but during the walking trials, to calculate the Achilles strain energy and the energy storage by using the same thing, the stretch of the Achilles tendon during stance phase, and then the Achilles tendon force as well. For muscle architecture, this is now an image of the medial gastroc. I apologize if the quality isn't quite great, but essentially this is how we kind of characterize muscle architecture. And so in the blue lines here, you can see these are the aponeurosis. This is the superficial aponeurosis. This is the skin up here, our muscle-related gastroc, and then our deep aponeurosis here. And muscle thickness we define as the distance between the superficial and deep aponeurosis, because that kind of encloses the muscle belly. Our yellow line here is a measured fascicle length. So that's where we measured fascicle lengths of the muscle for each of our contractions we did before they contracted and after they contracted. Then our pronation angle here you see is PA. That's the angle between the measured fascicle length and the deep aponeurosis, as you can see there. And so for muscle quality, we used the same image here of the medial gastroc. We've applied a filter to it. So this is now a histogram analysis that we used using image J. And what it does is it assigns a mean grayscale value to the tissue based on the intensity of their ultrasound waves that are reflected back from that tissue. And so what happens is different tissues have different composition, and based on their composition, they'll reflect back that ultrasound wave at different intensities, which is what you see reflected here. There's tissues that are shown in black are closer to a value of 0, and the more kind of white the tissue is, the higher the value it'll have in this analysis. And these kind of white or higher values are indicative of more fibrous or scar tissue than the muscle. It could be more intramuscular fat buildup, or even possibly inflammation or edema, are all things that have been implicated using this analysis. And so to look at estimated energy cost of walking, you can see again, here's a more close-up image of that metabolic mask we had there. And again, it was attached to a mixing chamber, then a metabolic cart. We were able to do those calculations. And so we looked at steady state. We wanted them to get to steady state oxygen consumption during the final 2 minutes. We can look at the expired oxygen or inspired oxygen, expired oxygen, carbon dioxide to look at energy expenditure. And we also did all of our other analysis in that same 2 minutes, looking at the muscle forces and the muscle tendon dynamics during the final 2 minutes of each phase or each walking trial. As I mentioned, we looked at energy costs through looking at the inspired and expired gases there. And we used that to calculate the rate of energy expenditure, which we were able to quantify as relative energy cost per unit distance, as you can see the units on the screen. And this suggests the calculation, the formula we used based off the previous literature to calculate the amount of energy they exposed, the amount of energy they were using up during the walking trials. In terms of muscle activation, during the walking trials, we also looked at using surface electromyography, so these little EMG sensors, that enables us to look at the amount of activation of some of these muscles during walking. And so you can see here a couple of sensors on the leg. This one's on the lateral gastroc. This one's on the fibularis longus. We also have them on the soleus and the lateral gastric names here. So lateral gastroc, soleus, tibialis anterior, fibularis longus. So these are all different muscles with different muscle actions. So 2 of them are plantar flexors, we flex the foot down. Tibialis anterior is dorsiflexor, so ox and opposition flows, and fibularis longus is an inverter of the ankle. And so we're kind of looking at different muscles across that joint that could be activating during gait. And what we're seeing here is those 4 muscles. This is just the raw signal across the different steps. So as they step, we'll activate these muscles differently. And how we analyze this was we filtered the signal and processed it, and then looked at the root mean squared of that activation. And then in a cyclical window for each stance phase, and we quantified activation of the muscle based on the amplitude of that root mean squared. We're also looking at the muscle tendon dynamics during walking as well. So here's another image of that medial gastroc here, as well as overlaid with the video of them actually stepping. And through that, we were able to look at a few different things. We were able to, again, visualize the muscle tendon shortening, elongation, different things with the fascicle, such as the length change during stance, shortening velocity, as well as calculating work and power of the muscle as well at each 5% of stance. And with that, we were also able to look at muscle energy cost, and we used this based on previously published values for sarcomere properties. And so we looked at energy costs based on the amount of number of cross bridges that would be required to produce the force that we measured, as well as the amount of cross bridge cycles that would be needed for the amount of shortening that we measured as well. So that's where we're able to estimate that energy cost. In terms of our eligibility criteria, we had participants self-report their HEDS diagnosis, and we confirmed a Baton score, which is essentially making sure they're classifying their joint hypermobility, as well as their symptoms. They had to be able to walk unassisted for 30 minutes as per our walking trial, and the control participants, we had a group of controls to compare them to, had to have a Baton score less than 4, which just means they weren't classified as having generalized joint hypermobility. So we had a non-hypermobile control group to compare to our hypermobile clinical group. And just for exclusion criteria, we didn't want to look at any other connective tissue disorders or any other prior cardiovascular, neurological, or musculoskeletal conditions that could influence the results, as well as any other medications that could affect or inhibit their response to exercise, or a positive response to that physical activity readiness questionnaire, which would signal they're not able to do the exercise we wanted them to do. For statistics, we did what we kind of call a more traditional approach, where we compared our 2 groups, our controls of our hypermobile or hypermobile EBS, across each of the 6 ankle angles for those MVCs, as well as across the 3 different speeds of walking. We used 2 ANOVAs to do that. And we also wanted to do an additional approach looking at our matched pair analysis. And so we matched our controls based on age and sex to our hypermobile participants. And we wanted to look at those differences in those matched pairs and see if there's more individualized changes there. As a group analysis, but could potentially wash out individual differences. As I mentioned before, the condition presents itself very differently for different people in terms of the severity, right? So we want to kind of capture that with our statistical approach as well. Then we use just basic literature values for calculating effect sizes, as well as an alpha level of less than 0.05 to look at statistical significance. So we'll talk about the results. First, the work related to the muscle weakness kind of side of the study, that dynamometer testing, and then we'll get to walking after that. For participants, we had a total of 22 participants participate, all in all. 11 of them had our diagnosis of HEDS, 11 were sex and age matched controls. You can see here our sex and age matching here, so there's the exact same ages between both groups, the same standard deviations. We age matched within a plus or minus 5 years to an EDS participant. You can see within each group, majority were females. We had 10 females and 1 male within each group, which again kind of reflects that the condition is more prevalent in women. And then height and weight, you can see were similar between both groups there. Looking at a few group comparisons. So range of motion wasn't different between both groups. This is referring to range of motion in the dynamometer, where we're looking at the different percentages of ankle joint range of motion. This is one that they actively set themselves. We weren't passively bringing them to any range of motion there. Moment arm was significantly larger in the EDS group, and so they had a larger moment arm from that moment arm measurement that I showed you. And Achilles tendon stiffness was significantly lower, so they had almost half of the Achilles tendon stiffness of the controls, and so significantly reduced tendon stiffness there. This is just showing a visual of the isometric contraction of the medial gastroc. And so they held this for about 5 seconds. As you can see here, that contraction there. We measured fascicle length, both before the contraction and afterwards to look at shortening as well. So it's, again, a really nice visual there. This is showing that stiffness that we just talked about there. So you can see here, despite a bit of variability within each sample, that we still had a significant effect. And it's again about half of the stiffness of the control group. So this is kind of showing that reduced Achilles tendon stiffness in our hypermobile group. We're talking about active and passive forces. What you're seeing here is those percentages of ankle range of motion we set in the dynamometer. So this 100% is maximum plantar flexion, 0% is maximum dorsiflexion. And we have active force here on the Y. So how hard can they push against that plate at each of those angles? You can see for any joint angle here, EDS shown in the black line here, they had a lower force. So they were weaker no matter where we measured them and across their ankle joint range of motion. Also notice here too that while the control group had their peak force at about 20% of their plantar flexion range of motion, EDS group reached that at a higher percentage of that. So they had an earlier peak force here, so at a different joint angle. And we'll see that more when we look at the fascicle lengths, how that looks. We'll look at the passive forces. So now let's look at the same x-axis here, but now passive force on the y-axis. You can see that for most of the range of motion, passive forces were pretty similar. As we get towards that maximum dorsiflexion here at 0%, you can see visually this looks like a bit of a difference. We have 300 newtons compared to about 400 newtons in the controls. But it's due to the variability in each sample, there wasn't statistical significance there. So no difference statistically in passive force. But when we look at the slope of this change, or what we denoted as being passive joint stiffness, that was significant. So despite the passive force not being significant, that change between 20% and 0% here was different between each group. So the joint was, in this case, less stiff for our hypermobile participants compared to our controls. Which again, you can see in the slope. Now we're talking about the fascicle length and then our estimated sarcomere length relationships with force. We're looking here at fascicle length on the x-axis, so shorter fascicle lengths on the left, going towards longer fascicle lengths on the right, and active force again on the y-axis here. And you can see again, similar as we saw before, that for any given fascicle length, the EDS group was weaker compared to the control group. And what's interesting here, as I pointed out before, in this case, their peak or optimal force that they have for the control group is at a longer fascicle length than the peak force for the EDS group, which was an interesting finding there. When we compare this to our estimated sarcomere lengths, and so again, these are estimations, and we didn't actually physically measure the actual tissues for sarcomere lengths, we just estimated it based on previous values. How we did that was we took peak force, when they found peak force, it's said to be associated with a sarcomere length of 2.64 micrometers. That's the length you can achieve the most maximum force. And so when we did that, we calculated essentially the change between fascicle length as a change between sarcomere length. We were able to plot the curves here. And you can see here, similar as this being the greatest kind of spot where there's the greatest disparity in force, and the most weak when controls were at their maximum force. That's reflected here. And so for a given participant, the maximum force they could produce was less in the hypermobile group. So they were relatively weaker compared to the controls. What's also interesting to note here is that the EDS group was having achieved longer sarcomere lengths based on our estimations here as well, which could be indicative of potentially fewer sarcomeres in series. Now that's based on estimations, so we can't confirm that based on this data, but it's an interesting implication. Also, you notice here at a sarcomere length of about 3 micrometers, they're producing similar forces between groups. There's certain kind of implications as well for what's going on at that muscle tissue level. But just kind of a big thing to highlight here again, that the biggest difference in force seems to be at when the controls were producing their maximum force, which is kind of a joint angle about 90 degrees. So kind of when I'm standing, My ankle's at about 90 degrees. That's the angle where they're producing the most force and controls. That's the angle where EDS seems to be the most weak for the ankle joint. When we look about explaining this muscle weakness, so now talking about those different factors we had before, the echo intensity, so that's that grayscale value of that black and white image of the medial gastroc. We can see that here on the y-axis, and it's a reminder that the lower values are indicative of better quality muscle tissue. You can see here that was a visual trend of the controls having better quality tissue. Just due to the variability, there wasn't a statistical significance here either. So based on the statistical approach, there doesn't seem to be a difference in muscle quality, although visually, it seems like there could be a trend. When we look at pronation angle, so pronation angle now on the y-axis here, you can see that there's virtually no difference at all between pronation angle for any given ankle position here. Same thing we saw for muscle thickness now on the y-axis. Muscle thickness also wasn't different between groups. And so these changes in muscle forces, the weakness that we observed, didn't seem to be due to differences in quality, pronation angle, or muscle thickness in this case. And so again, kind of summarizing these results in this part of the study, we know that we observed that they're weaker. We observed that these individuals with EDS were weaker and had that greatest disparity in force at optimal fast length for controls when that joint angles about 90 degrees. Why that's important is that can be a potential target for strength training for this population. If that's where their biggest disparity in strength is, that can now be a target to strengthen, close that gap, and potentially improve function. We noticed again, like I summarized, the weakness that we observed wasn't due to, at least in this sample, muscle size, muscle pronation angle, or muscle quality. Again, just within this sample, this is what we observed. Now to talk about the results from the second part of our study. So now we're talking about the walking part, where we're looking at muscle tendon dynamics and energy costs during the three different speeds of walking. And so we saw to look at pain and energy cost. We're looking at pain here on the y-axis, so that's 0 to 100 millimeters. On the x-axis, we're looking at this preferred walking speed, so 100% being a preferred walking speed, 80% a little bit slower, 120% a little bit faster. You can see right away there's a big difference between the groups. This is the control group in white, and then the EDS group with the black dots. So for any given speed, they had higher pain following that walking trial. What's also interesting to note here is that their preferred speed was one with less pain, which kind of makes sense. They're going to pick a speed to walk at, their preferred speed being the one that's the least amount of pain to walk at. When we look at energy costs, now we're looking at cost of transport here on the y-axis. And again, you can see that for any given speed, the EDS group had a higher energy cost to walk at that speed. What was also interesting here was that their preferred speed wasn't necessarily the most economical, where energy costs actually improved as their speed got faster, but the speed they chose as their preferred speed while having the least amount of pain actually wasn't the least amount of energy costs. And so that's just an interesting observation there as well. They actually were more efficient at the faster speed. When looking at the length change of the Achilles tendon during stance, there wasn't a significant difference between groups here. You can see by the overlap of these error bars. So they both kind of follow the same pattern of length change of that tendon during the stance phase. The stance phase, you can see here, we've broken it up into different 5% of stance. And so 0% would be heel strike, and then going all the way to 100% being toe off when the foot leaves the ground again. Similarly, when we look at Achilles tendon force during stance, while visually it seems to be that they're lower, the absolute measurements, there wasn't any statistical differences there. We know that relatively their maximum force was lower, so relatively there was weakness, but the absolute measurements didn't show a significant difference there. Then we look at the energy storage. So again, they were calculating that based on that length change of the tendon and based on the forces in the tendon. There wasn't a difference between groups in energy storage throughout the stance phase for any of the speeds. And so you can see that reflected here. These lines are overlapping a bit as well. When looking at the EMG data, we're going to look at the plantar flexors first here. So the lateral gastroc here and the soleus. You can see here we divided. I apologize, the wording's pretty small there. We had loading phase, so heel strike to about mid stance here, and then terminal stance when they toe off again. So these first three dots are stance phase. And then we have the initial swing and terminal swing phase here too. What was significant was during the stance phase, for both plantar flexor muscles, the EDS group had more muscle activation in the lateral gastroc and soleus muscle. So they're in those first three dots here. When we looked at the other muscles, so tibialis anterior or our dorsiflexor, and the fibularis longus, which is our everter, we didn't see those differences carry over there. What was interesting was we look at the ratio of our agonist and antagonist. So in this case, the ratio between the lateral gastroc and the tibialis anterior, as well as the ratio between the soleus and the tibialis anterior. That was significantly different between the groups, which could have implications for their walking strategy. What I mean by that is when they have, the ratio is about 1 for the EDS group. So if we think about, say, for example, my elbow, if my ratio between my biceps and my triceps is 1, there's not going to be a lot of movement there. It's activating the same extent, right? Whereas if it's less than 1, if my biceps overpower my triceps in this case, I'm going to see more movement. And so with that coactivation ratio of 1, they're having less movement and potentially a more stiffer strategy for gait. And so that was a really interesting finding there. Fascicle length changes during the stance phase. Again, you can see no changes there, very similar. With muscle force and fascicle work, same thing as Achilles tendon force. It looks like there could be a difference there. The absolute forces, there wasn't a statistical difference, but the relative force, so compared to their own maximum, they were weaker because their maximum force was weaker, as we saw before. Then we look at fascicle work. No differences across the stance phase there from 0 to 100% of stance. And so fascicle work wasn't different between both groups. And then we look at the muscle energy cost. So energy cost on the y-axis, percent stance on the x-axis. Also not different between groups, which makes sense if we didn't see any differences in length changes or forces through those calculations. It makes sense we wouldn't see differences in energy cost. And so despite having a higher total body energy cost, it doesn't seem to be due to differences in gastrocnemius muscle at least. So when we compare EDS controls with these findings, we did see differences in that through that lower Achilles tendon stiffness and lower muscular strength, which coincides with previous literature. We did see that ADS had greater pain at speeds other than the preferred walking speed, no matter if it was a slower or a faster speed, they had greater amounts of pain. And that the total energy cost of walking was actually better the faster they walked. So it wasn't necessarily their preferred speed, wasn't necessarily the most economical. Then that selection strategy focused on pain and energy costs, as I just kind of summarized there. And they might have this stiffer joint ankle strategy during gait to kind of keep the activation of plantar flexors and dorsiflexors pretty even, to kind of keep that joint stiffer and allow for less movement. We did see any differences, again, in tendon energy storage. So the amount of energy stored and released by the tendon during gait didn't change. Fascicle shortening wasn't different between both groups. Doesn't want to skip forward. Fascicle work didn't change, as well as muscle energy cost didn't change. So again, this highlights that if we're seeing differences in total energy cost of walking, if it costs more energy to walk, but it's not due to the gastroc muscle, if we didn't see changes in muscle energy cost, what else could be causing that? And so that's where we think it's most likely other joints in the kinetic chain, maybe possibly the hip joint. As you can think, if you're walking on a sheet of ice, for example, and you're trying to walk a little bit stiffer, you're going to have a lot more activation at your hips to try to kind of walk stiff, right? Like that. So we're thinking something similar could be going on with just the energy cost here. Some limitations from both the methods here. We did have a relatively smaller sample size with a large variance, right? So only 11 participants in each group, and again, that large variability in one of our measurements could have affected it. That could have also been in part due to differences in activity levels. Again, reflecting the differences within the severity of the condition. We had some participants who had a lot of trouble just walking on the treadmill, and some who were almost running and jogging on the treadmill. And so a really wide range of activity, like activity that they were able to do. And so future studies could potentially look at classifying participants based on the activity level a bit better. As well, our sample was mostly a little bit more of a young and active population. We had a couple who were older, but that also maybe doesn't quite reflect the true population as well. We had them self-identify as HDS, so we couldn't actually confirm their clinical diagnosis, but we could confirm their Baton score and their symptoms. This was an interesting point where our passive forces, remember we didn't see a difference in passive force when we measured the total joint, but we did see that decreased tendon stiffness. Now this is kind of an inherent thing when looking at whole body joint function, is that passive force is measured by every tissue that crosses that joint could be contributing to that. So anything that's going to resist dorsiflexion is going to contribute to passive forces. And so that might wash out that individual difference of the more compliant Achilles tendon. We did estimate sarcomere lengths. We didn't actually physically measure sarcomere lengths, or as our estimations there are a bit more speculative, but could lead for direction for future studies to look at that more in depth. And then for muscle quality, one of the things with that is the settings of your ultrasound really dictate that, right? So what your brightness is set to, your depth, your gain, that's all going to affect the brightness of those tissue, of the waves that are reflected back in the tissue. And so that makes it difficult when you're trying to compare these grayscale values outside to other studies and other populations. But within our study, we're interested more in just comparing our two groups and looking at muscle quality. So we know that our device has the same settings to make those comparisons. So now we're talking about what this means for really everybody that these results could impact, for patients with the condition, for clinicians who work with them, and for researchers like myself. So what does this mean for individuals living with EDS or HEDS? Well, we think that improving strength through that, especially since we saw that disparity in strength, might reduce the force required to perform daily tasks such as walking. We saw that in the relative force. And this might have implications for helping to improve symptoms such as chronic pain and fatigue. If we can reduce that strength gap, hopefully that'll have implications for improving function, improving symptoms. For the clinicians that work with these individuals, we know that weakness isn't not, at least in this sample, not due to muscle quality or atrophy. These are things that are commonly targeted for populations that are a bit more inactive, right? Let's increase muscle size, let's make muscle better quality. From this sample, this wasn't the case, and so this kind of narrows down our targets for rehabilitation for therapeutic exercise. Also, interestingly for clinicians too, their preferred walking speed is based on pain levels and not energy efficiency. So if we can actually improve pain, this might allow them to, select walking speed based on a more economically efficient strategy, which would then make the cost of doing these activities potentially better and improve symptoms like fatigue. If they can improve their pain, it'll cost them less energy to walk, hopefully, and from there, less fatigue and pain, hopefully, as well. And then what does this mean for researchers? Well, this allows us to look further into mechanisms of muscular weakness and what factors are contributing to these symptoms from a musculoskeletal level, right? We've kind of been able to rule out some things, at least from our sample. So it really leads into the future directions of this work. And so one is looking at other joints, such as the knee and the hip, to really look at how musculoskeletal factors are influencing function and symptoms. Looking at other measures of the muscle, such as cross-sectional area. Again, we just looked at one slice of muscle tissue thickness, right? So looking at cross-sectional area of the muscles, another area you could look at. Peripheral versus central activation. So really just looking at different areas of neuromuscular activation and how kind of a more neurological connection can influence muscular weakness. As well as digging further into those sarcomere properties, right? Ours were, like I mentioned this a few times, just estimations. And so looking further into the actual tissues themselves could provide some more clarity as what's happening at the tissue level. Now we see what's happening at the full joint level. And I quickly like to thank and acknowledge the team that we had working with this. It was very much a team effort with a lot of data to collect and analyze, as well as our participants. We can't do any of this work without our participants, and so we really thank them for participating in our study, as well as shout out from Mount Royal University for where we studied and did this collection. And yeah, just our funding sources were there to support our work. I'll do a quick plug for my PhD research. So we are still looking at EDS, in this case, the knee joint, and looking at how hormonal changes across the menstrual cycle can affect women with this condition and impact joint function and physical function. So if you're interested in learning more about the work we're doing right now, or anybody that might be interested in participating in the study, feel free to take a picture of the slide or reach out to me afterwards, and we can connect further. And with that, I'll wrap up my discussion portion here and open it up for any questions.
On the use pain at that specific, why did it reach that minimal there?
Really good question. I'll just repeat it for people online. So he was asking what we think influenced the lowest pain being at that kind of middle speed that they self-selected there. Why was that where the pain was lowest? And I think that it has to do with just how they selected that speed, right? We had them walk for 10 minutes, so then they could adjust the speed faster, slower, and pick what they think to be their preferred speed that they would like to walk, that they would usually walk at. And I think that, if you're living with chronic pain, you're going to prefer to walk at the speed with less pain, of course, right? Looking at it's going to do the most. And so I think by allowing them to self-select that kind of the pick the speed with the least amount of pain, because that's, well, one, that what they would typically do, and two, they knew they're going to do more walking trials with it, so that would also probably influence that way too. So I think just by how we measure that, how we let them define it, that's probably why it was the lowest, not the pain there. That answers your question.
Yeah, well, I'm kind of going into like, what would be the mechanism that at a set speed their pain would be?
What at a set speed their pain would be reduced, mechanism behind that. Yeah. I think that probably has to do with, well, we saw that their activation, levels are different. I'll go down that path. And so if they have a slower or a higher speed, that activation ratio, that co-activation ratio might be harder to maintain that co-activation ratio of 1, right? And so there has to activate my plantar flexors more, anything like that. Like it might require more muscle activity, and that would potentially be more painful if it's painful to contract those muscles, right? That's one reason potentially. It could also be due to just the fact that if that's the speed they're most comfortable at, that's the speed, they don't have to produce more force to walk faster. Like a faster speed, they're probably they might have to produce more force relative to the controls to walk at that faster speed. And so producing more force, more muscle activation there too, potentially more of that chronic pain if they're having to exert themselves more, right? So those are two potential mechanisms. I know it's kind of more surface level, but just based on our data, it was a little bit more surface level, I would say. So room to dig into more for sure, I would say, is the actual mechanisms behind pain and what manifests as pain here, right? So I think that could be a whole other research question of itself too, but thank you for the good question.
I just wonder what kind of pain they experience. Is it like chronic joint pain? Is it pain in the muscle? Pain around the tendon insertion, like tendinopathy? Like what? Because I think that could allow you to then think about what are the mechanisms, why are they changing different speeds, and whatever. Do you have a sense of like where the pain comes from and what the source is?
Really good question. The question was asking about kind of the type of pain they're experiencing, the source of the pain, whether it's joint pain, like more tendinosis kind of pain, right? So we didn't do a good job of capturing that for sure. Right? We just did the global pain level, like your pain level between each trial, marked on the 0 to 100 scale, right? And so we know that pain can manifest differently, right? Like nociceptive pain, neuropathic pain, different types of pain. And so, based on how you were to look at that, that could definitely change where we go down for the mechanism. In terms of this sample, a lot of it, I think, just quickly, is joint pain, more kind of chronic joint pain, just based anecdotally, without having those measurements behind it. Muscle kind of soreness as well is a big one, especially following activity. So more muscle soreness, chronic joint pain, I would say. But again, that's more anecdotal. We don't have the evidence here to back that up. Other studies that I've seen have looked at like tools that kind of dig into a bit further. Like there's questionnaires like the brief pain index that kind of further digs into that. Looking at, okay, which region of the body do you feel your pain the most? How would you describe it? Kind of asking those further questions to kind of get at that root. So there's ways to look at that for sure. We just didn't quite capture that enough here to really answer that question well. But anecdotally, it was more, they would complain of more joint and muscle pain to us at least.
Question back there. We're doing things randomized, I didn't capture it in the presentation, the order in which you did the different walking trials to see if that influenced pain.
So the question was, did we randomize the order of the walking trials to see if that influenced pain? We did randomize the order. So we had like the 80, 100, 120. So that was randomized for everybody. Because when you think about it, like by the third trial, pain could be higher. So you just walk for, at that point, 18 minutes. And if you're in pain all the time, your pain might be higher. And so that's why we randomized and hopefully control for that. And I think that's why we again see that kind of dip in the middle where we had that 100%, which wasn't everybody's first or last one. It was spread throughout. And so that kind of gives us a little bit more confidence to say that at that speed, that's when pain was lowest, when the other ones were higher. If that answers your question. Thank you.
So that pain and speed, is that for all participants or is it just for one participant?
So that was the average data between everybody. There was a bit of variation if I go back to it here. What slide?
Is that happening for everyone?
Yeah, so for all of our EDS participants at least, not one of them reported zero pain for the walking trials.
No, not, but that the pain goes at minimum for the
I see. Yeah, was it the same relationship for everybody? Yeah. On average, we saw that it was, I think for some individuals, they would have probably seen more because our deviation was a little bit big for that too, right? And so for some individuals, there'd be less of that dip. It would have been pretty constant, whereas for others, it would have been a more exaggerated dip. That's why we kind of see that kind of balance that one in the middle. And so I think, again, by factor of it being such a range of severity for the condition, you have some individuals that are more affected and have more pain at the different speeds, maybe even the higher one, like faster one more so, and some individuals that just aren't as affected by walking speed, which is why you see that big variability there. Does that answer your question?
Yeah. And does that mean that if we have more pain, we have to spend more energy on that?
I would say not necessarily, because they had more pain at the 80, it's based on our data alone. Whether it was 80 or 120%, they had higher pain, but their energy cost went straight down from 80 to 120. And so despite the faster speed being more economical in this case, it was still more painful, right? And so it's not quite necessarily directly coinciding, it seemed, at least in our sample. I know more globally, maybe there's a different relationship going on, but at least in these, 22 people, it seemed that, the energy cost of a certain speed and pain weren't necessarily related to each other more so, they were just selected for differently, if that makes sense. Yeah, of course, good question.
Thanks, Donald. First of all, thanks for such a comprehensive study and presentation. It's kind of crazy how many measurements you did here. One thing that's kind of stuck out was the difference in moment arms, and it actually seemed quite big. I'm wondering if there's an anatomical explanation for that, or if you think this is a function of inaccuracies in the tendon excursion method and having clearly different tendon mechanical properties that could sort of influence that.
Very good question. The question is asking about the differences in moment arm and kind of the reasons behind that, whether it's more anatomical or issues with the measurement itself. I think that when we think about the measurement itself, like the range of motion was similar, and so like we're thinking about the angle change, that'd be somewhat similar, but with our tendons, if they're more compliant, they're going to have potentially that different elongation, right? So it's a challenging one. It's one that I've spent some time thinking about. We didn't quite capture length of the different components of the leg, right? And so we can't really look at shank leg versus whole leg length versus height. We got just height, and height wasn't different between groups, so it wasn't difference based on height. You know, mechanistically thinking about the tissue, you know, maybe a more compliant tendon does bias a larger mobile arm just because it's gonna elongate more potentially, but we didn't see that in our data. We saw the stretch was similar between both, right? And so I don't think that's the case. Again, I think it's one that we don't have a clear explanation for based on our data alone. It might take, you know, more work to look at. Let's look at, you know, the tissues itself and look at kind of more again, the tissues, all the tissues contributing to that passive force. So again, we look at the force we used to look at moment arm was all the tissues of the ankle joint that's resisting dorsiflexion, not just the Achilles tendon, right? And so there could be differences, you know, in the tendon, but that may not actually come about with all the tissues in the joint. And so there's a couple different kind of layers to it that we're not quite capturing, I don't think. So the easy answer is I don't know. But
Yeah, well, I encourage you to keep thinking about the inaccuracies of the tendon excursion method. And, because I do think that that's playing a role.
Yeah.
If those moment arm differences were, which were quite large, if those were real, then I feel like that'll start to shake out when you start looking at the tendon elongations during walking and at least the estimated force production of the tendon during walking, the E and G activation and stuff like that. And then I guess along those same lines is, I feel like I ask this question in this place all the time. So you want to increase strength to maybe change the way that they walk or change their pain or whatever. What are in the people with HEL?
HEDS.
Okay. What are the strength values in relation to the moments that they have during walking? You know what I mean? Like, if you increase their strength, is that really gonna help them walk? If the moments required to walk are significantly lower than their strength?
Really good question. So again, just thinking about, you know, moments required to walk in versus the actual strength measurements. It's a really good question. I think that, you know, the absolute values of moments, you know, weren't different, right? Whereas the relative strength was. And so that does beg the question of, you know, are we targeting the right thing if we're trying to improve, in this case, symptoms and function? Maybe muscle strength isn't the only target to look about. Thinking about more, again, things that a lot of this data we have here is kind of ruling things out, right? Like it wasn't muscle quality, it wasn't muscle architecture. In this case, there's no changes in the moment or the energy cost of this muscle. So what other things were going on throughout the rest of the kinetic chain during gait, right? Maybe we don't target the ankle joint, but because there's no differences in the plantar flexion moment. Maybe we look at different joints in the kinetic chain, which again requires further studies, further research. But no, I think it's a really good point to think about, you know, what the data is telling us in terms of measuring something in one area, not quite translating to what we're seeing in the other area, for sure. So appreciate that.
Jared, did you have a question or comments about that?
I was just gonna follow up on Brand's comment about the moment arm and excursion method. So can you remind us who are maybe aren't familiar with the tendon excursion method, how you rotated the joint and whether passive moments were present?
So I'll try and back that
In
slide.
other words, does tendon compliance matter when you make this measurement?
Great question. So when we take this measurement, sorry if everyone's gonna get dizzy here. I forget what number of slide it was. There we go. So kind of how we're taking this measurement is we're rotating them passively in a dynamometer from their max dorsiflexion set to the max plantar flexion. And then what we're doing with this method is we're looking at, well, one, the amount of elongation of the tendon, and two, the amount of change in the ankle joint angle there is, right? And we're looking at this within a 10-degree range. So from the 85 degrees to 95 degrees, that's kind of like the bottom end of this equation, right? And then we're looking at how much displacement was there, that tendon junction, across those 10 degrees during that passive rotation. And so again, could be some assumptions there for sure, and issues with this method, especially when we know that this is impacted at the structural level, right? Maybe this method is fine for those with, you know, typical, let's say, collagen, right? But potentially there could be some overestimation there when you have a more compliant tendon, if it's more prone to increase. But we didn't see differences here, right? Like we didn't see differences in that elongation of the tendon. And so I guess it might not have been due to that we saw that increase.
No, you did, right? You brought them through the same angle. You changed an angle, so it must have been in the differences in the length.
Yeah, good point.
But I think what Jared's trying to get at is, in theory, if you're doing this right, you shouldn't really have any passive force contributions, because you're bringing it through the range of motion.
Mhm.
So the question is, why would the connective tissue, in this case, really have an influence on the measurement?
But let me
I think it
let me
is.
make a comment before we go on, because what you're saying, I'm not sure what you exactly measured,
Mhm.
but what you're saying cannot be correct. Because if you really measure the tendon elongation as a function of joint angle, then any elongation that the muscle would be undergoing would be neglected, which means you would underestimate the moment arm.
Mhm.
So I'm not sure what you measure, but if it's actually tendon elongation and you completely neglect that the muscle gets a bit longer as well, then you did something wrong.
Yeah, because we were measuring essentially kind of the point, where it identified from our image, like where the tendon meets the gap. So yeah, we wouldn't have accounted for any changes in the muscle unit itself, just at that point of where, essentially this point here, we kind of just followed that throughout and looked at change at that point. And so we wouldn't have accounted for muscle length, I guess, in that case.
Very early in my student life, I was involved in a study where they measured moment arms about the ankle joint, the average was about 5 centimeters. I had 58 millimeters, and your values are 44 and 37. And I'm not sure, maybe because most were women and they might have smaller moment arms, but for adults, those are actually small moment arms that you measured. So I wondered about that.
Yeah, it's an interesting one for sure. And again, it could be, again, like you said, the point which we measured, is it based on just like physically how do we measure said point? Maybe that influence the lower measurements, right? Or like you said, like anatomical differences compared to different values. But yeah, probably based on where we chose that point and where we chose to follow the tissue, influence those lower moment arms probably.
I think you have to, I mean, I've tracking the aponeurosis too, I don't really know what else you would track. Then there's probably changes at the calcaneus that you're not measuring, right? So there is error, but what's interesting is if you look at these kind of measurements and you compare them to the same people, where you look at the moment arm in like an MR machine, this method always underestimates the moment arm, always. And so I still think if everything's perfect in the setup, I still think there's some passive structural force contributions to the thing that can influence it. And that's not getting at anything that Walter's talking about, like whatever the muscle's doing. I didn't even think about that really.
But two different points that are equally valid, right? Like those are just things that we didn't quite capture in the way that we measure the moment arm, And so since the moment arm was something that we used with all the force measurements too, if we had some issues there, that could have also impacted not seeing differences later on during the activate, like looking at those moments and then the forces as well, right? So yeah, definitely things to consider methodologically, yeah, and thinking critically about how we did it. So I appreciate both those thoughts.
I have a quick question
Mhm.
for Walters. So you had one male participant in each of your groups, right?
Yes, yeah.
Did they show anything like completely different than all of your females?
There wasn't really a clear outlier. It was kind of right in the mix with everything else. Like there wasn't really a clear one to identify. We could have, I guess we could have split it between, looking at just the male pair versus the, but even when we looked at the matched pair analysis, like the differences between that pair were similar to the female pairs. So there wasn't really a clear sex difference when we were doing the analysis, and so that's why we grouped it all together when we reported it. And so that, I guess, does that answer your question?
I just thought maybe they did something completely different, or the trend in their response to the actual syndrome was different, but that.
I mean, it seemed to be that there wasn't a trend, at least from our sample of 1 in 10, right? I know that, there are trends, sex-specific trends in the condition themselves, where more pain, worse like pain symptoms, even joint injuries do sometimes follow a cyclical cycle for women compared to men. But we didn't capture that really at all. Like looking at a single time point, we didn't really capture really any kind of changes between men and women in that sense, I guess. Yeah.
Walter, you had a question?
Yeah, but few, methodological questions, but before I go there, I want to acknowledge how difficult these things are, but I'm not trying to criticize, I'm just trying to understand how you actually did things. So for example, how did you calculate the medial gastrocnemius force?
So that one, we essentially calculated, I'm trying to remember how we did this 3 years ago. We had the moment arm from essentially
in detail,
yeah,
maybe conceptually.
yeah. So conceptually, we had essentially this on the foot plate, but also in the sole of the shoe, so we compare moments during walking. And we use an approach where we know the distance, and we know from this is essentially kind of a pressure sensor within the insole. So we know exactly the center where they're applying their force here. And so we take whether it's center where they're applying the force, and then the moment arm of the insole itself, and we compare that to our measured moment arm of the, in this case, the Achilles tendon, and then we use that equation to say the forces here are equivalent to the forces being produced from on the other side, and with the muscle tendon in that case. I think is how we did it.
So, yeah, and I mean, that would make perfect sense, but then you have the muscle force from the entire triceps surae group.
Yes.
And I thought you said that you calculated medial gastric lesion.
Yes, so in that
How did
case,
you do that?
yeah, so we took a literature value for the physiological cross-sectional area of the medial gastroc of about 0.17. I forget the actual units behind that, but essentially we tried to account for when we looked at active force, it was total plantar flexion moment. Then we looked at the fascicle, the medial gastroc specific force. We tried to account for that by having that literature value of here's the cross-sectional area of the medial gastroc compared to the rest of the triceps surae, and using that to divide our force by. So then we have the force contribution of that in theory. We couldn't actually measure the cross-sectional area, but
You assumed, essentially you assumed constant contribution, a constant like 17% or whatever. Of the total moment will be produced by the medial gastroc.
I mean, assume that for all of our participants. And so again, if that was different per participant, that could have again influenced why we didn't see differences in some places, but that's what our assumption we
And
made.
also it would be interesting if that actually, I would assume that might also change as a function of joint angle, depending on what the force length relationships are of the individual muscle.
I would assume so. And I think that's another reason why, you know, going forward, if I was to do this study again, to look at like more than just one slice of the muscle element or something, look more at the cross-sectional area to again kind of account for those differences more, right? But we were only operating really on just one section of that tissue. And so I had to make some assumptions, I guess, in our calculations based on that. But yeah.
The other thing that was interesting is when you were with the one group, you know, you had sarcomere lengths, average sarcomere lengths that were a little bit more than 4 microns at the longest lengths. And you still had about 50 or 60% of the maximum force. So purely based on overlap, you would expect it to be 10 or 15%. So do you have an explanation why you get so much more force than theoretically you would be expecting?
Yeah, so that's one that again, we were scratching our heads on for a bit. And again, it's limited because again, we're looking at, when we look at the measured Lefasco lengths, we have that. When we look at the sarcomere length at that angle, we're estimating, which has some assumptions there too. But there's been one study we came across where it was looking at biopsies from the quad muscle in patients with a slightly different subtype of EDS, this tenacin X deficient EDS. So a slightly different subtype than we're looking at. But what they found was when they stretched out those sarcomeres from that participants, they actually had increased passive force from tighten at longer sarcomere lengths, which they attributed to differences in like the stiffness and the elastic kind of of tighten there. And what they attributed that to being is that when you have these kind of extracellular changes in tissue stiffness, where whether it's the Achilles tendon, so the anterior component that's more compliant, or even the compliance of like the parallel elastic component of the muscle, that there's an adaptation in the muscle cell itself in the sarcomere to increase stiffness through tighten to accommodate for that. And that from their study, they showed that higher force at longer lengths was attributed to by that increased passive force from tighten in that study.
I thought that was active force that you were showing.
So
that was
Yeah.
total force. But
That was
if it's
total
total
force.
force, then it makes perfect sense.
that in that case would have been total force for that angle. So it was active
I
force.
think you labeled it active.
So this is the slide I was talking about with the passive sarcomere lengths, but I want to go to. Here we go. So this case, it was the active force. And then this was their active force relative to the EDS relative to the controls,
Yeah.
active force, right? And so in this case, we're looking at total triceps surae force and not the individual muscle gastroc. So again, that means there's some assumptions here as well. So doing total triceps surae for the one muscle.
Yeah, no, I'm just looking at, you know, on the left, on the right there, you know, you're at 4 microns or a little bit
Mhm.
longer. And then when I look at that data point on force, you know, that's 1400 and the peak is about 1600. So you are very close to peak, whereas I would expect it to be 10% or 15% based on overlap.
Mhm.
If it's active force, if it's total force, then of course I don't know.
And I think again, too, with our active force, like when we did look at active force, we did our total force and subtracted our measured passive force during the passive trials. But again, that's not going to capture any passive forces like at the tissue level. It's going to be the whole joint level, right? So there's some assumptions there in our calculations of active force and taking out the passive forces, right? So again, I think we just some assumptions when we take the whole joint measurements down to the tissue level, I think we just gotta make some assumptions there that probably get lost in translation, I would think.
A couple more questions, but if other people want to jump in quickly.
Are there other questions before?
I have a very quick question.
All of them.
I was curious about, morphological properties of the tendon. Did you measure cross-sectional area or resting length? And if so, did you see?
We did get cross-sectional area, sorry. With the tendon just based on, where our ultrasound probes were, we could really only just get, like elongation of the tendon and length changes. Just because we had, the medial gastroc, we had the junction of the tendon. And so really we kind of just saw the proximal end of that tendon and the changes in that, right? And so we couldn't really get a measure of its tendon length itself. We have like fascicle length at rest, and that wasn't quite different. But we don't quite have that for the tendon, just based on how we collected the data. We just don't have that information.
Do you know if that changed from other studies in people in the clinical population?
I know that the stiffness definitely has been reduced by other studies.
Yeah.
Cross-sectional area, I think tendon thickness. I'd have to review the literature, but tendon thickness, I'm pretty sure they've seen is lower in this population, because some of the proposed interventions have increased tendon stiffness and tendon thickness, and thereby also stiffness. And so I would speculate that it's lower, but again, I'd have to brush up on my literature to really answer that one well, but really good question.
Brent?
I just wanna know about their bones. Did they have bad quality bones?
So again, we didn't measure anything bones here,
No,
but in the
I know,
literature,
I
I
know,
know.
yeah.
But
Yeah.
literature wise, actually, there's a few things coming out now looking at how there is poorer bone quality in these individuals. Well, it's one of the outcomes of this condition is a lower bone quality, right? And whether that's due to disuse of just lower physical activity or being sedentary, it's kind of still
Thinking about
conjecture.
the impact of the college.
And that's the thing too, I haven't read a lot on, like development of bone development to see how it's impacted there, but if the connective tissues are impacted from a developmental standpoint with collagen, and then I would assume that bone also being, made up with collagen, would also see some impacts there. But I don't know that literature well enough to really speak well to it. I just know that overall bone health has been seen as a poor outcome in the condition. But it's an interesting thought to bring that collagen to any, because really it's any tissue with collagen, really, right? It could be affected here. But I don't know enough to speak on it confidently.
Aaron had a question.
Can you go back to the slide where you showed the formula for energy?
Yes, I can. That should be this one.
Yeah, so what made you decide to use the formula rather than using your breath by breath analysis? And then I'll just back that up with, could you have then used that to quantify the walking economy?
Great question. So why we use this formula versus breath by breath? The short answer is, I don't know if I can tell you why, because we did this 3 years ago and I forget the exact rationale as to why. I think it just let us do, based on, this literature value, we we're able to just get a quick measurement of it, right? We could quickly look at energy costs there. In terms of, looking at walking economy, I think you definitely could with the data we have. I think that might be somewhere along the lines of what we're looking at and analyzing for our manuscript based on this. But I don't know enough, again, myself, I haven't read this literature in a while, to actually speak to why we chose this and the pros and cons of this equation versus the breath by breath approach. I don't know if I can tell the pros and cons of why we did this versus that. I apologize.
I think Jared wants to answer the question.
So you took the steady state VO2 in the final 2 minutes, so you averaged the breath by breaths, all of them over 2 minutes. And that's your VO2 from your equation and your VCO from your equation to get energy, which is a measure. Joules per kilogram per meter in walking economy.
Yeah, so I guess, the breath by breath, we're assuming to be similar over those 2 minutes because we have a steady state of oxygen. Yeah.
Any other questions before I go back to Walter? Well,
You talked about measuring, quantifying the storage of energy in the tendon. Did you also measure the release and calculate the hysteresis by any chance?
That's a really, I don't have those numbers with me here. I don't know if we did or didn't. But I think that if energy storage wasn't different, we had no difference in storage, no difference in change in rate. So I'd be curious if that just reflects there's no differences in hysteresis. We definitely could calculate with the numbers we have. I just don't know if I haven't seen it myself with our data yet. But I would speculate that if we're not seeing differences in energy storage itself, or differences in length change of that tendon, I'd speculate it might be similar. But again, I don't have those numbers, and we didn't actually calculate that at this point, I don't think.
I mean, the hysteresis will give you an idea about the viscosity, and I was wondering if, you know, the viscous properties of the normal tendon and the disease tendon that you look at,
Yeah.
that might potentially be different.
So I think that would be an interesting implication, right, if the viscous properties are different, right? Because especially,
You know, if you have more energy loss, let's say, in the disease tendon, that might hint at some, why it might cost more energy is, yeah.
Mhm.
The other thing that I had was, you know, the tendon in the disease state is less stiff, but then the overall stiffness that you measured, I think, was about the same, you said? Of the muscle tendon comp, or no, I should say it differently. Yeah, did you measure the overall stiffness of the muscle tendon complex?
So I think for stiffness, we just had,
Because I thought
tendon,
you showed it for the whole, in the muscle excursion, you know, you.
yeah, so that one we showed for so it's the kind of same region we took stiffness from, for the ABC, we looked at length change of that muscle tendon junction. During walking, and so we used that to look at Achilles tendon length change. And that was kind of our forces there. So we didn't look at the whole muscle tendon unit per se. It was more that muscle tendon junction and how much elongation was based on that throughout throughout walking essentially.
I was just thinking, you know, if you have the muscle and the tendon, you think it was two springs in series, then, you know, if the tendon is less stiff, but the muscle would be a bit stiffer because of some connective tissue or whatever, then the overall stiffness might actually be the same. And I was just wondering if you try to also look if there was a difference in the stiffness of the muscle.
We didn't look at that per se, I don't think, but I think it's a really good point to think about, right? Especially if we're only basing our measurement off of, you know, 1 point for stiffness. We're 1 point between two springs almost, right? And so we're not quite capturing that as well as we could, I think. So we did, short answer is we didn't quantify the muscle stiffness itself. And so again, that could be missing out on some more potentially differences here, maybe.
Is there any indication that the muscles are different?
Based on,
aside from the force that you measured and those type of things?
yeah, I mean, there was some hints that the quality could be different based on that, but the variation was so huge that we didn't see on anything. I know from like literature values, there's been some looking at, I haven't seen a lot looking at like connective tissue, like within the muscle itself, like the parallel and series stuff, or like in the circuit. There's actually been a lot.
Fibrosis or.
I haven't come across a lot in my readings. I would say that because there's also the different types of EDS. There's been a lot more research into like the classical subtype of EDS or the vascular subtype, looking at tissue properties there. I know in the classical subtype, where they actually have more like the like cauliflower-like collagen, where actually the structure is different. And in that you have differences in terms of like the actual tissue qualities and stuff themselves. But there hasn't really been the same type of approach in the hypermobile subtype. So I don't think there's enough of the data out there to look at it. There's more like say fibrosis, for example, and stuff. I haven't seen a lot for that.
Just the last comment, you know, but when you showed that the video of the muscle contracting and you showed the fascicles and the angle of pennation, in the video that you showed, the angle of pennation seems to get really, really big. And I was wondering if you looked at the angle of pennation, there, so at the very end there, it's a very big angle of pennation. I mean, I would guess like, I don't know, 60 degrees or so, maybe even a bit more.
And again, it's changed too, but based on the person, and if there were slight differences in where we placed our ultrasound too, on the muscle belly, could have influenced differences in information between people too. And there was big variation there as well. Like in each of our measurements of like the muscle architecture, there was quite a bit of variation. And so I suspect this could be someone who had larger pennation angles, right? And that could have skewed the measurement.
Is this a normal person or is this a disease?
This one is a hypermobile EDS participant. Yeah.
Anyway, just so. Thanks.
Oh, thank you for the questions. I appreciate it.
Any last question before we thank Donald again?